How many times have you decided to study, full of motivation to learn, open your material, and just a few minutes later found yourself holding your phone without even noticing, scrolling, answering messages, or thinking about something completely different? And when you finally realize it, time has slipped away, your concentration is gone, and you're left with that bitter feeling of frustration. Do you know why this happens? It's not because you lack discipline, and it's not because the subject is too difficult. The truth is, the world we live in today was designed to steal your attention. Phones, notifications, short videos, instant pleasures, every one of these things is training your brain, day after day, to chase quick rewards and run away from deep effort. And it's not just harming your studies, it's affecting your personal and professional life. Look around you. The modern world is a distraction machine. The phone buzzes every second. Notifications pull your focus. Pleasures are always one click away. We are surrounded by invisible obstacles that may seem harmless, but destroy your ability to concentrate. In ancient times, humanity's biggest challenges were war, hunger, disease. People had to fight to survive, endure the cold, and protect themselves from danger. Today, most of us don't face those threats daily. Our war has changed. Our battle is no longer against hunger or armed enemies. Our battle today is against social media that hijacks your attention, against the endless stream of stimuli that addict your mind, against the instant pleasures that kill your discipline. And you know what's even more dangerous? The modern world doesn't just rely on your natural weaknesses, it was designed to exploit them. The algorithm is working against you. It watches every click, every second you spend scrolling, every tiny pause of curiosity. And what does it do with that information? It feeds you exactly what it knows will hook you. It recommends what makes you procrastinate, what distracts you, what keeps you glued for hours without building anything meaningful inside of you. This is the silent war that most people never even notice. So how can you expect to have discipline to study, to work, to create, if every single click on what distracts you weakens your ability to stick with the things that require effort? The real enemy is not the complexity of what you want to learn. It's the simplicity of what pulls you away from it. The algorithm is like an equation engineered to exploit your curiosity against you. And the only way to win is to do the opposite, to consciously choose what you expose your mind to, the way a scientist chooses the data he allows into his experiment. Because distraction is one of the greatest battles of modern life. So how do you break this cycle? How do you escape this invisible trap that trains your mind every single day to get distracted? Listen carefully. The key is not to eliminate social media completely. The key is to redirect it. Because the same platform that weakens you today can also be used to strengthen you. Instead of clicking on everything that gives you cheap pleasure, start seeking content that elevates you, teaches you, and strengthens you. Bit by bit, the algorithm will adapt. It will begin recommending what feeds your mind instead of what drains your energy. Simple? Yes, but almost nobody has the discipline to do it.
And here's the powerful truth. You don't need to abandon social media entirely. You need to transform it into a training ground. Instead of following pages that only distract you, follow mentors, follow thinkers, follow people who share ideas that expand your vision. Instead of consuming passively, turn every video into a starting point. Take notes, explain it out loud, apply it in practice. Don't fight against curiosity, direct it. The mind will always seek stimulation. Your power lies in choosing which kind. The secret is not to kill this instinct, but to guide it. If you direct your curiosity toward content that nourishes instead of drains you, you begin to train the algorithm to work for you, not against you. If you flip the switch and decide that every click is a vote for the future you want, the very system that holds you back today will start to push you forward. That is the difference between being a victim of the algorithm and using it as an ally in building your success. But listen closely. It's not enough to simply understand the problem. You need a system. Because if you keep relying on willpower alone, you will lose. You need structure. And all of this begins with discipline. Discipline is the key. Imagine this. Every day you wake up and you don't depend on motivation. You know exactly what to do, how long to focus, and how to apply what you've learned. That is the power of a daily focus system. The first thing you need to understand is this: the human brain cannot maintain absolute focus for hours on end. That's an illusion. Forcing yourself beyond your natural limit only creates frustration. The secret is not quantity, it's quality. So remember this formula: 40 minutes of deep focus, 10 minutes of intentional rest. That's the ideal cycle. 40 minutes is long enough to dive into a subject without exhaustion. 10 minutes is the pause your mind needs to recharge before the next round. Push too far, and your mind scatters. Rest too long, and you lose your rhythm. But it's not just about setting time. It's about clearing the ground before you begin. Ask yourself, what is distracting me every day? It could be your phone, an open social media tab, or even a cluttered desk. Each of these is a silent thief of energy. And here's the truth: every time you let a distraction into your space, your mind learns that it doesn't have to respect focus. You are training yourself to be distracted. So, rule number 1, your phone stays out of the study environment, not in your pocket, not face down on the desk, out of the room. If you need it as a tool, use apps that block notifications and limit access to distractions. Rule number 2, a clean desk. Everything in your field of vision competes for attention. Keep only what you'll use for that block of study. This signals to your brain that there are no escape routes. Rule number 3, focus questions. Before starting each cycle, write on a sheet of paper, what exactly do I want to understand in this block? This eliminates vague studying, the kind where you turn pages aimlessly. Clarity is the trigger for focus. Now, during those 40 minutes, practice something almost nobody does: active attention. That means not just reading, but engaging with the material. Take notes, ask questions, create examples. And when your mind starts to wander, and it will, don't fight the thought. Simply jot it down on a piece of paper. Distraction, pay the bill, call someone back, and then return. That simple act frees your mind because it realizes it doesn't need to hold on to that thought. During those 10 minutes of rest, don't make the fatal mistake of opening social media. That destroys the cycle. Rest must be active. Stand up, drink some water, walk around, stretch. This sends oxygen to your brain and signals that you're taking care of your body while your mind organizes what it just absorbed. And here's a detail almost nobody talks about. It's not only about how long you focus, it's also about what you cut. If you're losing hours every day to the same kind of distraction, you need to realize that it's not just a pastime, it's an addiction. Pay attention to the patterns. Which app do you open most? At what time of day? And what emotion triggers the escape? Is it boredom? Anxiety? Fear of not understanding? When you identify the trigger, you can cut the problem at the root. And here's a truth that can change everything. You don't need to be perfect. You need to be consistent. If you simply do 3 blocks of 40 minutes a day with proper breaks and strong boundaries against distractions, in 1 month you'll produce more than most people do in 6. Pay close attention to me now. Focus is not magic, it's engineering. It's the way you design your environment, your cycles, your habits, so that distraction doesn't even get a chance. If you're dominated by it today, it's not because you're weak, it's because you haven't built the right system yet. Build that system, and your mind will start to obey like a precise instrument, ready to take you to extraordinary results. But none of it matters if you don't have discipline. Knowing focus techniques, study cycles, or learning strategies means nothing without it. Focus is like a flame. You can light it today, but without discipline it will be gone tomorrow. Discipline is the daily fuel that keeps that flame alive until knowledge is finally turned into results. Discipline means doing what must be done even when you don't feel like it. It's sitting down to study when your mind craves distraction. It's completing the 40-minute block when everything inside you wants to quit. It's explaining out loud what you just learned even when nobody is there to listen. It's repeating until your mind understands that there's no negotiation. And here's the hard but liberating truth. Discipline is not prison, it's freedom. Because while most people live enslaved by distractions, impulses, and moods, the disciplined person is free. Free to choose what to learn. Free to build the future they want. Free from depending on luck or outside circumstances. Now imagine what happens when you bring the 2 pillars together.
trained focus, and unshakable discipline. You don't just learn faster, you become someone who cannot be shaken, who doesn't sabotage themselves, who moves forward every single day despite criticism or difficulty. And it is exactly this consistency that the world rewards, with opportunities, with respect, with prosperity. In the end, it's not just about studying better. It's about building a mind so strong and so disciplined that no distraction can stop you. And when you reach that level, you'll realize something extraordinary. Success in any area of your life is no longer a matter of luck. It's only a matter of time. And the real power doesn't come from bursts of motivation, but from becoming methodical. The human mind responds to patterns, to repetition, to system. When you plan your study routine and decide exactly what you're going to do, you leave no space for excuses. You take away the burden of deciding and leave only the task of executing. And here's the key: start small. Don't try to become a genius in a single week. If today you can study for 15 minutes with full attention, start with 15. Tomorrow, push it to 20, then 30. The size of the step doesn't matter, the consistency does. What trains your mind is not the intensity of a single day, but the discipline of repeating every day until your mind learns to obey. Be methodical. Set the time, the place, the duration, and the specific goal. Don't just sit down to study anything. Write down: today I will understand this chapter, this concept, this technique. That creates a mental contract. And when you honor that contract, your mind begins to trust you. It realizes that when you say, "I will," you follow through. And that's when self-confidence is born. Imagine this. Within a few weeks, you won't even need to struggle so hard to concentrate. Your mind will enter study mode almost automatically because you've trained it. You've taught your brain that there is a specific time of day when there are no negotiations, no distractions, no excuses, only commitment. That is the invisible force that turns ordinary people into extraordinary ones. Commitment means honoring what you planned, even when you don't feel like it. And that's exactly what shapes your identity. Every time you complete a daily goal, no matter how small, you send a powerful message to yourself. I control my mind, not the other way around. That is true freedom. Not doing things only when you feel like it, but because you decided. And the most impressive part is the compound effect. Small blocks of study, repeated day after day, create an exponential growth curve. What once seemed impossible to learn begins to feel simple. What used to take great effort becomes natural, because the mind, when trained, learns to obey. So remember this: the secret is not short bursts of intensity, it's method. It's not starting huge, it's starting small and never failing. When you become methodical, when you create a clear routine and stick to it, you'll realize there's no limit to what you can learn. Success in any area of life becomes nothing more than an inevitable consequence. Now it's your turn to act. Write in the comments, "I have focus." That simple phrase will reprogram your mind to believe what you declare. And every time you repeat it, you strengthen your commitment to success. And remember, focus is the key, but positivity is the fuel. A positive mind finds solutions where others only see problems. Before you leave, hit the like button and subscribe to the channel. That simple action proves to yourself that you are committed to this transformation. Thank you for watching, and I'll see you in the next video.
If you close your eyes and picture energy, you probably imagine some kind of glowing blue fluid, or a crackling lightning bolt, or maybe a shimmering aura that flows from a battery into a light bulb. You think of it as a stuff, a substance, a blob of something that moves from place to place. I hate to be the one to ruin the magic trick, but that is completely wrong. In physics, today, right now, we have no knowledge of what energy is. We do not have a picture that energy comes in little blobs of a definite amount. It is not a fluid, it is not a gas, it is not a ghost inside the machine. So what is it? It is a number. That's it. It is a mathematical quantity. It is an abstract bookkeeping rule that nature, for some reason, decides to obey. Here is the situation. There is a fact, or if you wish, a law, governing all natural phenomena that are known to date. There is no known exception to this law. It is exact so far as we know. We call it the conservation of energy. It states that there is a certain numerical quantity, which we call energy, that does not change in the manifold changes which nature undergoes. That is a most abstract idea because it is a mathematical principle. It says that there is a numerical quantity which does not change when something happens. It is not a description of a mechanism or anything concrete. It is just a strange fact that we can calculate some number, and when we finish watching nature go through her tricks and calculate the number again, it is the same. Imagine a bishop on a chessboard. If you look at the red squares, the bishop is always on a red square. You can move it, you can dance it around, you can distract it. But if you count the number of bishops on red squares, that number is conserved. Energy is like that. It is a rule of the game, not a piece on the board. To understand this, we have to stop thinking like physicists and start thinking like a mother dealing with a very mischievous child. Imagine a child. Let's call him Dennis, the menace. Dennis has a set of blocks. These blocks are absolutely indestructible and cannot be divided into pieces. Each is the same as the other. Let us suppose that he has 28 blocks. His mother puts him with his 28 blocks into a room at the beginning of the day. At the end of the day, being curious, she counts the blocks very carefully. She discovers a phenomenal law. No matter what he does with the blocks, there are always 28 remaining. This continues for a number of days, until one day there are only 27 blocks. Now, does she assume the law of conservation of blocks is broken? No. She investigates. A little looking around shows that there is one under the rug. She must look everywhere to be sure that the number of blocks has not changed. One day, however, the number appears to change. There are only 26 blocks. Careful investigation indicates that the window was open, and upon looking outside, the other 2 blocks are found. The accounting works. The number is saved. Another day, careful count indicates that there are 30 blocks. This causes considerable consternation until it is realized that a neighbor boy came to visit, bringing his blocks with him, and he left a few at Dennis's house. After she has disposed of the extra blocks, she closes the window, does not let the neighbor in, and then everything is going along all right, until one time she counts and finds only 25 blocks. This is where it gets interesting. There is a box in the room, a toy box, and the mother goes to open the toy box, but the boy screams and says she is not allowed to open it. So now she has a problem. She has 25 visible blocks. She is missing 3. She suspects they are in the box, but she cannot see them. The energy is hidden. Being extremely curious and somewhat ingenious, she invents a scheme. She knows that a block weighs 3 ounces, so she weighs the box at a time when she sees 28 blocks, and it weighs 16 ounces. The next time she wishes to check, she weighs the box again, subtracts 16 ounces, and divides by 3. She discovers a formula. The number of blocks seen plus the weight of the box minus 16 ounces divided by 3 ounces equals a constant. In the graduate, there then appear to be some new deviations. Careful study indicates that the dirty water in the bathtub is changing its level. The child is throwing blocks into the water, and she cannot see them because it is so dirty. But she can find out how many blocks are in the water by adding another term to her formula. Since the original height of the water was 6 inches, and each block raises the water 1/4 of an inch, this new formula would be the number of blocks seen plus the weight calculation of the box plus the height of the water minus 6 inches divided by 1/4 inch equals the constant, 28. In the gradual increase in the complexity of her world, she finds a whole series of terms representing ways of calculating how many blocks are in places where she is not allowed to look. As a result, she finds a complex formula, a quantity which has to be computed, which always stays the same in her situation. Now, what is the analogy of this to the conservation of energy? The most remarkable aspect that must be abstracted from this picture is that there are no blocks. Take away the first terms in our equations, and we find ourselves calculating more or less abstract things. The analogy has the following points. First, when we are calculating the energy, sometimes some of it leaves the system and goes away, or sometimes some comes in. In order to verify the conservation of energy, we must be careful that we have not put any in or taken any out. Second, the energy has a large number of different forms, and there is a formula for each one. These are gravitational energy, kinetic energy, heat energy, elastic energy, electrical energy, chemical energy, radiant energy, nuclear energy, mass energy. If we total up the formulas for each of these contributions, it will not change except for energy going in and out. But remember, there are no blocks. We don't know what the mechanism is. We just know that if we take the speed of a car and square it and multiply by the mass and divide by 2, we get a number. And if we take the height of a rock and multiply by the weight, we get another number. And if we measure the temperature of a radiator, we get another number. And when we add all these seemingly unrelated numbers together, the total stays constant. It is an abstract thing in that it does not tell us the mechanism or the reasons for the various formulas. It just works. Conservation of energy can be understood only if we have the formula for all of its forms. Let's start with the simplest one, gravitational energy near the surface of the Earth. I wish to derive this formula in a way which has nothing to do with history, but is simply a line of reasoning to give you an illustration of the remarkable fact that a great deal about nature can be extracted from a few facts and close reasoning. Consider weightlifting machines, machines which have the property that they lift one weight by lowering another. Let us also make a hypothesis that there is no such thing as perpetual motion with these weightlifting machines. That is, if we have lifted and lowered a lot of weights and restored the machine to the original condition, we find that the net result is to have lifted a weight. Then we have a perpetual motion machine because we can use that lifted weight to run something else. We assume this is impossible. If you could build a machine that lifts a heavy weight by dropping a light weight a short distance and then resets itself without using fuel, you would be a billionaire. But nature is stingy. She doesn't allow it. Imagine a very simple weightlifting machine, a lever or a pulley. This machine lifts weights 3 units strong. We place 3 units on one balance pan and 1 unit on the other. However, in order to get it actually to work, we must lift the little weight off the left pan. On the other hand, we could lift the 1 unit weight by lowering the 3 unit weight, if we cheat a little by lifting a little weight off the other pan.
Of course, we realize that with any actual lifting machine, we must add a little extra to get it to run. This we disregard temporarily. Ideal machines, although they do not exist, do not require anything extra. A machine that we actually use can be, in a sense, almost reversible. That is, if it will lift the weight of 3 by lowering a weight of 1, then it will also lift nearly the weight of 1, the same amount, by lowering the weight of 3. We imagine that there are 2 classes of machines, those that are not reversible, which includes all real machines, and those that are reversible, which of course are actually not attainable, no matter how careful we may be in our design of bearings and levers. We suppose, however, that there is such a thing, a reversible machine, which lowers 1 unit of weight by 1 unit of distance, and at the same time lifts a 3 unit weight. Call this reversible machine, machine A. Suppose this particular reversible machine lifts the 3 unit weight a distance x. Then suppose we have another machine, machine B, which is not necessarily reversible, which also lowers a unit weight a unit distance, but which lifts 3 units a distance y. We can now prove that y is not higher than x. That is, it is impossible to build a machine that will lift a weight any higher than it will be lifted by a reversible machine. Let us see why. Let us suppose that y were higher than x. We take a 1 unit weight and lower it 1 unit height with machine B, and that lifts the 3 unit weight up a distance y. Then we could lower the weight from y to x, obtaining free power, and use the reversible machine A, running backwards, to lower the 3 unit weight a distance x, and lift the 1 unit weight by 1 unit height. This will put the 1 unit weight back where it was before, and leave both machines ready to be used again. We would therefore have perpetual motion if y were higher than x, which we assumed was impossible. With those assumptions, we thus deduce that y is not higher than x, so that of all machines that can be designed, the reversible machine is the best. We can also see that all reversible machines must lift to exactly the same height. This is a very remarkable observation,
because it permits us to analyze the height to which different machines are going to lift something without looking at the interior mechanism. We know at once that if somebody makes an enormously elaborate series of levers that lift 3 units a certain distance by lowering 1 unit by 1 unit distance, and we compare it with a simple lever which does the same thing and is fundamentally reversible, his machine will lift it no higher. So, what is this distance, x? Suppose we have a reversible machine which is going to lift this distance x, 3 for 1. We can prove by logic alone that x must be 1/3 of a foot. The generalization is clear. 1 pound falls a certain distance in operating a reversible machine, then the machine can lift a certain amount of pounds, this distance divided by that amount. Another way of putting the result is that 3 pounds times the height lifted, which in our problem was x, is equal to 1 pound times the distance lowered, which is 1 foot. If we take all the weights and multiply them by the heights at which they are now, above the floor, let the machine operate, and then multiply all the weights by all the heights again, there will be no change. We call the sum of the weights times the heights gravitational potential energy, the energy which an object has because of its relationship in space relative to the Earth. The formula for gravitational energy, then, so long as we are not too far from the Earth, is the weight times the height. It is a very beautiful line of reasoning. The only problem is that perhaps it is not true. After all, nature does not have to go along with our reasoning. For example, perhaps perpetual motion is, in fact, possible. Some of the assumptions may be wrong, or we may have made a mistake in reasoning, so it is always necessary to check. It turns out experimentally, in fact, to be true. The general name of energy, which has to do with location relative to something else, is called potential energy. In this particular case, of course, we call it gravitational potential energy. If it is a question of electrical forces against which we are working, instead of gravitational forces, if we are lifting charges away from other charges with a lot of levers, then the energy content is called electrical potential energy. The general principle is that the change in the energy is the force times the distance that the force is pushed. But this is just the beginning. We have only talked about statics, things standing still. What happens when things move? Where does the potential energy go when a pendulum swings down to the bottom? The gravitational energy disappears when it is down at the bottom. Nevertheless, it will climb up again. The gravitational energy must have gone into another form. Evidently, it is by virtue of its motion that it is able to climb up again. So we have the conversion of gravitational energy into some other form when it reaches the bottom. We call this kinetic energy. And just like with the blocks, we need a formula for it. We need to find where the blocks are hiding when the object is moving. And trust me, the formula for motion is where things start to get really messy. We left off with a nice, tidy picture of the universe. We had weights and heights. We had reversible machines. We established that if you lift the rock, you are storing a number, gravitational potential energy. But the universe refuses to sit still. What happens when you drop the rock? As it falls, it loses height. The gravitational potential energy is vanishing. The number on our balance sheet is dropping towards 0. If the law of conservation of energy is real, if those indestructible blocks haven't simply ceased to exist, they must have gone somewhere. They must be hiding. Look at the rock just before it hits the ground. It has no height left, but it has something else. It has speed. It has motion. If we attach that moving rock to a rope and a pulley system, its motion can pull another weight up. It has the capacity to do work. The energy didn't disappear. It shape-shifted. It turned into kinetic energy. Now we need a formula for this. We need to know how many blocks are hidden in a moving object. Recall our arguments about reversible machines. We can see that the motion at the bottom must correspond to a quantity of energy that permits the object to rise back to a certain height. It doesn't matter how it got that speed, whether it fell from a cliff, was shot from a cannon, or was pushed by a rocket. Motion is motion. When we do the math, we find a specific rule. To find the kinetic energy, You take the weight of the object, multiply it by the square of its velocity, and divide by a constant related to gravity. Notice that's squared. That is critical. If a car goes twice as fast, it doesn't have twice the energy, it has 4 times the energy. This is why high-speed impacts are so much more violent than low-speed ones. The number of hidden blocks explodes as you go faster. So now we have 2 places to hide our blocks. In height, potential, and in speed, kinetic. Is that it? Is the universe just things going up and down and fast and slow? Of course not. Nature is far more devious than that. Consider a spring. If you pull down on a spring, you are doing work. You are sweating, pulling against the metal. You hold it there. The spring isn't moving, so there is no kinetic energy. It hasn't changed height, so there is no gravitational energy. Yet you know there is energy there. If you let go, it snaps back. It can lift weights. It can smack you in the face. We have to invent a new term, elastic potential energy. This is the energy stored in the tension of the spring. But wait, there is a problem, a flaw in our beautiful reversible machine logic. We cheated. Throughout this entire explanation, we have been assuming that machines go on forever. We assume that a pendulum swings back up to exactly the same height it started from. We assume the spring bounces forever.
But you know that's a lie. If you swing a pendulum, eventually it stops. If you bounce a spring, eventually it settles down. When the pendulum stops, it has no height. It has no speed. The potential energy is 0. The kinetic energy is 0. The numbers are gone. Did the blocks disappear? Did nature finally break the law? Where did the energy go? This brings us to the most brilliant hiding spot of all. Heat. Inside the spring, inside the pendulum, inside the air they move through, there are crystals and molecules made of billions of atoms. When things move on a large scale, like a car rolling or a pendulum swinging, we try to be very delicate. But nature is messy. There is friction. There is bumping. As the motion slows down, the visible kinetic energy disappears, but the invisible kinetic energy appears. The atoms inside the material start to jiggle. They start to wiggle in a random, confused manner. We lose track of the energy on the macroscopic scale, but it is still there. If you put a sensitive thermometer on a spring that has just stopped bouncing, you will find it is warmer. That warmth is the energy. Heat energy is not a new thing. It is just kinetic energy, internal motion, hidden in the chaos of the crowd. This is a profound realization. It means that what we call heat is just the kinetic energy of atoms that are too small to see. The blocks didn't vanish. They just got chopped up into dust and scattered among the atoms. But if you could count the motion of every single atom, the total number would still be exactly the same. Once you accept that energy can hide in the jiggling of atoms, you start to see it everywhere. There is electrical energy. This has to do with pushing and pulling electric charges. There is radiant energy. This is light. We know light carries energy. It heats up the pavement. It burns your skin. Light is just a wiggling in the electromagnetic field. There is chemical energy. This is the energy released when gasoline burns or when you digest food. But what is it really? It is just the electrical energy of atoms attracting and repelling each other. It's the same rules, just deep inside the chemistry. There is nuclear energy. This is the energy involved with the arrangement of particles inside the nucleus of an atom. We have formulas for it, but honestly, we don't fully understand the fundamental laws of it yet. And finally, there is the monster, the one discovered by Einstein, mass energy. It turns out that an object has energy simply from its sheer existence. Even if it is sitting still at absolute 0 temperature with no height and no electric charge, it has energy because it has mass. If you take a positron and an electron and you bring them together, they disappear, they annihilate, and out comes radiant energy, light. You can calculate exactly how much. The formula is the mass times the speed of light squared. This means mass and energy are the same thing.
Mass is just a very, very dense way of storing the blocks. So, where does this leave us? We have a law, conservation of energy, that seems to be absolutely true. We check it in steam engines, in stars, in atoms, and in galaxies. The number always balances. The blocks are always found, whether under the rug, in the toy box, or in the jiggling of atoms. But remember what I said at the beginning. We don't know what energy is. We do not understand energy as counting little blobs. It is a mathematical quantity. It is abstract, and it gets stranger. In quantum mechanics, we learned that this conservation law is actually related to time. It turns out that conservation of energy is just the physicist's way of saying the laws of physics don't change depending on what time it is. If you do an experiment today and you do it again tomorrow, nature behaves the same way. That symmetry in time is what causes energy to be conserved. Energy is not a substance. It is the shadow cast by the consistency of reality. Before we finish, I have to give you a warning. I told you that energy is conserved. That implies we can never run out of it. So why do we worry about saving energy? Why do we pay electric bills? Because while energy is conserved, useful energy is not. There is a lot of jiggling around in the atoms of the sea. The ocean has a massive amount of heat energy, but you can't get those atoms to herd together and drive a ship unless you have a temperature difference, unless you take energy from somewhere else.
Nature doesn't care about us. She has conservation of energy, but she spends it in all directions. The sun liberates massive amounts of energy, but only a tiny fraction, 1 part in 2 billion, falls on the earth. The rest is lost to the void. Our job, the job of the physicist and the engineer, is to figure out how to catch those blocks before they get hidden under the rug of entropy. We get energy from the sun, from rain, which comes from the sun, from coal, which is stored sunlight, and from uranium. If we can figure out how to control thermonuclear reactions, fusion, we could get enough energy from 10 quarts of water per second to power the entire United States. It can be done. The blocks are there. We just need to be smart enough to find them. So the next time someone talks about energy, don't picture a glowing blue fluid. Picture a child hiding blocks. Picture a number that refuses to change. And remember that even though we can't touch it, and we don't really know what it is the one thing in this universe that we can count on.
June 1974. Richard Feynman stands at a podium facing Caltech's graduating class in their caps and gowns. These students have just completed degrees from one of America's most prestigious science institutions. They're expecting the usual commencement speech about reaching for the stars and changing the world. Instead, Feynman tells them that most of what passes for science, including research published in respected journals, taught in university courses, and funded by major institutions, is fundamentally worthless. He calls it cargo cult science. And then he explains why even they, despite years of rigorous training, are probably guilty of practicing it. This comes from Feynman's documented 1974 commencement address at the California Institute of Technology, later published as Cargo Cult Science, and preserved in the Caltech archives. The speech would become one of his most cited warnings about the corruption of scientific thinking. But the story starts much earlier, in the South Pacific during World War II. During the war, Allied forces built airstrips on remote islands across the Pacific. Cargo planes would land, bringing supplies, medicine, food, technology. The indigenous islanders watched these metal birds descend from the sky and unload treasures beyond imagination. They saw the patterns. Soldiers would sit in towers with headphones, speaking into devices. Men with paddles would wave their arms in specific sequences. Runways had to be cleared of debris, and then, reliably, the planes would come. After the war ended, the planes stopped coming. The soldiers left, the supplies disappeared. So the islanders, using pure logic, decided to bring the planes back. They cleared strips of land to create runways. They built control towers from bamboo. They carved headphones from wood and wore them while sitting in the towers. They fashioned antenna shapes from straw. Men stood on the runway waving palm fronds in the same patterns they'd seen the soldiers use. Every element was replicated with stunning attention to detail. The form was perfect. The planes never came. They had everything that looked like an airstrip, everything that appeared to be the conditions for cargo planes to land. But they were missing something fundamental, something invisible. They didn't understand radio waves or flight mechanics or military supply chains. They had copied the form without understanding the substance. To an outside observer, it looked exactly like an airport. To the planes that never came, it was meaningless. Feynman stood at that podium and told those graduating students they were doing the same thing. He wasn't talking about obvious pseudoscience or fringe conspiracy theories. He was talking about published research in academic journals, studies conducted by credentialed scientists at legitimate institutions, work that followed all the apparent rules of scientific methodology, papers that got cited in textbooks, and yet, Feynman argued, most of it shared the same fundamental flaw as those bamboo headphones. It looked like science without being science. Consider one of his examples. For years, researchers studied whether rats could learn to navigate mazes faster with each subsequent attempt. Hundreds of experiments were conducted, papers were published, debates raged in psychology journals. Different research groups claimed different results. Some found dramatic learning effects, others found none. The field churned out study after study, each following proper experimental protocols, each with control groups and statistical analysis. Everything appeared rigorous, but Feynman noticed something. When a researcher finally conducted an experiment accounting for whether the rats could actually hear or smell their way through the maze, not just see the visual cues everyone had been measuring, the learning effects vanished. For decades, researchers had been inadvertently allowing rats to use sensory information no one was controlling for. Every previous experiment, despite following the form of good science, had missed this fundamental variable. The papers weren't fraudulent. The researchers weren't stupid. They had the appearance of scientific rigor, but they lacked what Feynman called scientific integrity. This reveals something crucial about the difference between methodology and integrity. You can follow every rule, cite every source, use every statistical tool correctly, and still produce garbage if you're not honestly trying to disprove yourself. The cargo cult scientist runs the experiment. The real scientist tries to think of every reason the experiment might be fooling them. Feynman gave another example that hit closer to home for physicists. Robert Millikan's famous oil drop experiment measured the charge of an electron, fundamental work that won him the Nobel Prize in 1923. Millikan reported his value with high confidence. His published data showed beautiful consistency. But here's what Feynman discovered when he dug into the history. Millikan's first published value was slightly off. As subsequent physicists tried to replicate his work, they kept getting values slightly different from Millikan's. Each researcher would get a number, compare it to Millikan's prestigious result, assume their own methodology must be flawed, adjust their procedure, and eventually publish a value closer to Millikan's. The next researcher would do the same. For years, the scientific community slowly crept toward the correct value through this chain of partial self-deception. Each physicist thought they were being rigorous. Each followed proper experimental protocols. Each had good reasons to trust Millikan's earlier work. But collectively, they were practicing cargo cult science. They had the form of verification without the substance of genuine independent testing. They were unconsciously tuning their results to match expectations rather than measuring reality cleanly. Feynman emphasized this wasn't about dishonesty. Most cargo cult scientists are sincere. They believe they're doing real science. The problem runs deeper than fraud. It's about a type of self-deception so subtle you don't notice you're doing it. He described it this way. The first principle is that you must not fool yourself, and you are the easiest person to fool. That sentence from the 1974 address cuts to the heart of cargo cult thinking. Your own brain actively works against you seeing your mistakes. You notice evidence that confirms what you believe. You unconsciously discount evidence that contradicts it. You run the experiment until you get the result that seems reasonable, then stop. You interpret ambiguous data in the direction you expect, and every step feels like you're being objective. This wasn't just about scientific research, but about any field where intellectual honesty matters. Cargo cult thinking appears everywhere, in business, in education, in journalism, in policy making, in your own work. Whenever you're going through the motions of rigor without the substance of genuine truth-seeking, you're building a bamboo control tower. Back to that commencement address. Feynman told those graduates about scientific integrity, which he defined as bending over backwards to show how you might be wrong, not just following the rules, not just being thorough, but actively searching for the ways your own conclusion could be mistaken. He said scientists should give all the information that could call their results into question, not hide contrary evidence in footnotes, not emphasize data that supports their hypothesis while downplaying contradictions. Put the ammunition for your critics right in the abstract. He gave a specific instruction. If you're doing an experiment, you should report everything that you think might make it invalid, not only what you think is right about it. Most researchers do the opposite. They report what supports their conclusion and briefly acknowledge limitations only if forced to. They have reasons. They need publications to get tenure. They need funding. They want their ideas to be taken seriously. Every incentive pushes them toward emphasizing confirmatory evidence and minimizing doubt. The system rewards cargo cult science because cargo cult science produces cleaner narratives, more confident conclusions, and easier to publish papers. Real science is messy. It's full of uncertainties and contradictory data and results that don't make sense. Papers that honestly report all that messiness often look weaker than papers that smooth over the complications. So researchers learn to build bamboo control towers, studies that look rigorous but are actually exercises in selective presentation. But then Feynman went further. He told those graduates that they had a responsibility beyond their own research. They needed to refuse to participate in cargo cult science even when everyone around them accepted it, even when it cost them professionally. He said, "You will not only do no particular good, but if you have any reasons for a feeling of pride on the basis of your accomplishment, you will lose it." That's a devastating message for a commencement speech. You spent 4 years earning this degree, and now you're being told that simply following the norms of your field will make your work worthless and drain your accomplishment of meaning. But Feynman wasn't trying to discourage them. He was warning them about the specific trap that catches people who think they're too educated to fall for obvious nonsense. The cargo cult islanders can be forgiven. They had no framework for understanding radio communication or aerodynamics. They were doing their honest best with limited information. But a physicist who cherry-picks data, a researcher who stops investigating once they get the result they wanted, they know better. They have the tools to recognize their own self-deception. They just choose to ignore those tools because building a real control tower is harder than building one from bamboo. Consider how this applies today when you're evaluating expertise. Someone has a degree from a prestigious institution. They've published papers in respected journals. They use sophisticated technical language. They present data in compelling visualizations. They cite sources. Every marker of legitimate expertise is present. But are they practicing cargo cult expertise? Are they selectively presenting evidence that supports their preferred narrative while burying contradictions? Are they mistaking the appearance of rigor for actual rigor? The same principle applies today when you're doing your own knowledge work. You research a topic. You find sources that support your existing belief. You organize them into a coherent argument. You anticipate objections and prepare responses. You present your conclusion with confidence. You've done everything that looks like thorough analysis. But did you genuinely try to prove yourself wrong? Did you seek out the strongest counterarguments, or just the ones you could easily refute? Did you update your belief when you encountered contradictory evidence, or did you explain away that evidence to preserve your original conclusion? Most people go through life building bamboo control towers without realizing it. They follow career advice that sounds sophisticated, but they never verify whether it actually produces results. They adopt productivity systems that feel rigorous, but never track whether their actual output improves. They learn frameworks and models and methodologies that give them the appearance of expertise without the substance of genuine understanding. They're not being dishonest. They genuinely believe they're being thorough, but they're fooling themselves. Feynman had seen this pattern throughout his career. During the Manhattan Project at Los Alamos, he watched brilliant scientists get so invested in their theoretical models that they ignored experimental data, contradicting their predictions. After the war, he saw academics build entire research programs around fashionable ideas that crumbled when subjected to genuine scrutiny. He noticed how institutions incentivized the appearance of productivity over actual discovery, how funding favored projects that promised clear outcomes over genuine exploration, how peer review rewarded papers that fit expected patterns over papers that challenge assumptions. And he recognized the trap catches everyone eventually, including him. He told a story about his own early research where he'd gotten excited about a result, only to realize later he'd been unconsciously interpreting ambiguous data in the direction he wanted. He hadn't committed fraud, he'd just been human. The experience taught him that intellectual integrity requires constant vigilance against your own motivated reasoning. This brings us to the deepest layer of what Feynman was warning about. Cargo cult science isn't just methodologically flawed research. It's the betrayal of science's fundamental purpose. Science exists to be wrong less often, not to be perfectly right, not to achieve absolute certainty, but to gradually, painfully, honestly reduce the ways we fool ourselves about reality. Every scientific practice, peer review, replication, controlled experiments, statistical analysis, exists as a defense against human self-deception. When you go through the motions of those practices without their spirit, you've kept the shell and killed the organism. You're waving palm fronds on a bamboo runway, wondering why truth won't land. Feynman ended his commencement address with something unexpected. He didn't give those graduates a rousing call to action or an inspirational message about changing the world. He told them they'd probably face a choice at some point in their careers. They could practice cargo cult science, publish regularly, get funding, build a respectable career, gain the respect of peers who are doing the same thing. Or they could practice real science, which might mean publishing less, struggling for funding, being seen as difficult or uncooperative, and possibly never achieving conventional success. He couldn't tell them which to choose. He could only explain what each path meant. 36 years before that speech, in 1938, those Pacific Islanders were still building their bamboo airports. They believed with complete sincerity that they were doing everything necessary to bring back the cargo. They'd be heartbroken to learn they were wasting their effort. But at least they didn't know better. They lacked the framework to understand their mistake. You don't have that excuse. You know the difference between going through the motions and genuinely trying to be less wrong. You know when you're selecting evidence to support your conclusion versus following evidence wherever it leads. You know when you're adopting the appearance of expertise versus building actual competence. You feel the difference, even if you don't admit it. The question Feynman left hanging in that speech hall was simple. Which runway are you building? The one where planes might actually land, even if it takes longer and looks less impressive. Or the bamboo version that photographs well but serves no real purpose except maintaining your illusions. Because here's what he understood that most people miss. The cargo cult version feels like it's working. You're busy. You're productive. You're following best practices. You're accumulating credentials and publications and recognition. The activity itself creates the illusion of progress. The planes never come, but you're so focused on waving the palm fronds that you don't notice. Real science, real expertise, real understanding, it often looks less impressive from the outside. It's slower. It's full of dead ends and mistakes and uncertainty. It requires saying, "I don't know," more often than feels comfortable. It means abandoning ideas you invested years in when the evidence contradicts them. It offers fewer guarantees and more humility. But it's the only kind that works when reality comes to evaluate your conclusions. The only kind that builds something lasting instead of decorative. The only kind that brings actual planes to actual runways instead of maintaining comfortable delusions about bamboo. Feynman gave them one last piece of advice before they walked across that stage to receive their diplomas. I'm talking about a specific extra type of integrity that is not lying, but bending over backwards to show how you're maybe wrong that you ought to have when acting as a scientist. That extra type of integrity. That's the piece missing from the bamboo control tower. That's what separates real understanding from its convincing imitation. And that's what he was challenging them, and challenging you to carry into whatever work matters to you. The planes still aren't coming to those bamboo runways. They never will. But somewhere, someone is building a real airstrip, with all the invisible complexity that requires. Where are you building yours?
Imagine for a moment that learning a language was like learning to take apart a radio, just without getting shocked. And imagine that instead of spending hours in painful classes trying to look smart, you only needed 15 minutes a day. This isn't some mystical promise from a spiritual guru with a relaxing voice and purple lights behind. It's physics applied to your mind. Consistency plus understanding equals the miracle of the human brain, or as I like to call it, using your brain the way it was actually designed to be used, instead of treating it like a walking flash drive. Pay close attention now, because this matters. Most people try to learn a language by memorizing rules and word lists. That's like trying to learn how to swim by reading a book on the beach. You might look busy, you might even sweat, but once you're in the ocean, you sink like a very ambitious rock. The key isn't memorizing, it's understanding. The brain hates useless effort. It loves patterns, connections, and living context. So if you want to learn a language, the game is not repeating words like a proud little parrot. The game is creating meaning, even if at first it feels like someone threw random syllables at your face. Now you might be thinking, but I don't understand anything in the beginning. Great. Congratulations. You're alive, not an encyclopedia. Confusion isn't the enemy. It's the lobby of understanding. That's where you train your brain to say, relax, I'll figure this out. This is the fatal mistake most people make. They run away from confusion. But you should embrace confusion the way a scientist embraces a strange equation. Because the moment it starts making sense, your brain pops a bottle of champagne and goes, I knew I was brilliant.
Learning a language isn't about talent. It's about building familiarity, listening to and reading the same short passage several times, letting your mind chew on it quietly, the same way it processes anything important. And here comes your first epiphany. Speaking is a consequence. It's not the start of the process. It's the bonus that comes when you're so soaked in the language that it slips out of your mouth without asking for permission. Now let's shape all this into a routine. A routine so simple that the only way to fail is not showing up for 15 minutes. And I know you can show up. Imagine opening a simple book in the language you want to learn. Nothing epic, nothing like starting Russian with Dostoevsky on day one, unless you enjoy emotional collapse served with a cup of tears. You pick a tiny passage, not a full chapter, not a 2-hour lesson, 30 seconds of text, maybe 1 minute of audio. You'll look at it, listen to it, and think, I didn't understand anything. Excellent. Your neurons just woke up. The brain hates the unknown, and that's exactly what forces it to learn. You read it once, slowly. Then you listen. Then you read again, and the words start to look a little familiar. Still can't speak? Perfect. Richard Feynman didn't know physics when he was born either, and that turned out fine. With each repetition, something magical starts happening. Loose pieces begin to organize themselves. A word here, a phrase there. The mind creates hooks. This is real learning, not memorizing, recognizing. When the brain recognizes, it keeps. Notice something. You're not memorizing, you're not suffering, you're not feeling stupid. You're exploring. Explorers don't recite lists of trees, they enter the forest. And now comes the point where most people quit. But I can't stand repeating the same thing over and over. If you think like this, congratulations. You've just described the exact reason you've never gotten great at anything before.
Smart repetition is like watering a plant. You don't dump 10 liters of water at once and hope for the best. You water a little every day, 15 minutes. It's not about quantity, it's about continuity. Now let's get to the method, exactly what to do in those 15 minutes. Before you even start the clock, one rule. Your material must have text plus audio. No audio only in the beginning unless you want to rely on luck and chaos. Now we start, your actual daily ritual. And yes, ritual. If it were just a technique, everyone would use it. A ritual has presence, it has weight, it has that quiet sense of this matters. So do this with me now, mentally if you're on the bus, physically if you have enough dignity and privacy at the moment. Minute 1, brain priming. Don't pick up the material yet. Take 3 slow breaths. This isn't mysticism, it's neural signaling. You're telling your brain, stop, we're learning now. Without this, you study with the same focus as someone reading a medicine label after too much coffee. Let me ask you something. Have you noticed how much better your brain works when it knows where it's heading? That's the explorer mode. If you don't activate it, your brain stays in survival mode, and everything feels way harder than it should. Minutes 2 and 3, light exposure. Now yes, grab your tiny passage. 30 seconds of text or 1 minute of audio, nothing more. You're not here to prove intelligence, you're here to build controlled, familiarity. Read without trying to understand everything. Look at it the way a scientist looks at a strange phenomenon, curious, not desperate, like someone who says, interesting, even when they have no idea what they're seeing. This is where 90% of people quit, because they want to understand before they look. But in the real world, understanding comes after looking, after repeating, after looking again. This is your advantage now. You know confusion is a doorway, not a failure. So read. No pressure, no translating yet, just exposure. 2 minutes and done. Yes, done. Want to continue? Great. Can't? No problem, because tomorrow you're back, and your brain will be waiting for you, and curious like a cat chasing a laser. From here on, we start building progressive comprehension, one step at a time. Mountains are for the ego. Staircases are for people who actually reach the top. Get ready. The next step is where your brain starts recognizing patterns almost without your permission. Now that you've looked without panicking, we go deeper. Minutes 4, 5, and 6. Brain-text synchronization. Read the same passage again. Yes, the same one. This time with the audio playing. Read and listen at the same time. Your brain will freak out a bit, like it's trying to watch a movie while solving an equation, but then it thinks, wait, I know this. I think I'm getting it. That tiny spark is the miracle. It's the moment when neurons whisper, connect, yes, almost. You're not trying to speak yet. You're not memorizing it. You're not torturing yourself with grammar. You're absorbing rhythm, tone, sound, movement. Think of it like tuning an instrument before playing, or listening to music before trying to sing. And yes, I know, your ego wants to impress the world and start forming sentences right now. But your brain is, and saying, relax. Let me teach you the difference between sound and noise first. You're training perception. Speaking comes later. Understanding comes now. By the end of 6 minutes, you've seen the text twice, heard it twice, and your brain is doing its secret magic, turning chaos into meaning. And here's what you're avoiding: the fatal trap of language learning, thinking that learning is collecting words. Learning is organizing meaning. Most people try to store loose words like someone trying to store dust in a drawer. You're building structure. Congratulations. You're learning like a scientist, not a parrot. From here, we'll reinforce that structure the way you build a rocket, in layers. Now we reach the point where your brain truly starts working on its own. You've read the text, you've heard it with the text. Now let's test your mind without training wheels. Minutes 7, 8, 9, and 10. Just listening. No looking at the text, no reading, no panic, just listen. Now yes, I know, your mind is about to tell you that you're terrible at this, that you didn't understand anything, and that maybe learning Esperanto would have been easier than this. Ignore that emotional child inside you. It's just confused by the effort. Do this with me right now, mentally. Close your eyes for 2 seconds and imagine you're listening to someone speak in another language. But now, instead of trying to translate everything like a panicked lunatic, you simply listen. Notice the rhythm, the cadence, the melody of the sentences, the way words begin and end. If you try to translate everything, you fail and you suffer. But if you observe it like a scientist watching atoms dance, or like someone listening to gossip with zero context but full curiosity, your brain starts to deduce meaning. That's how babies learn. Have you ever seen a baby say, "Father, please present me the full verb conjugation chart"? Of course not. They observe, imitate, throw sounds into the air, and let chaos work in their favor. Now actually do this. Take a phrase in another language that you roughly understand. Repeat it in your mind without translating it word for word. Just let the phrase exist. That's your training for today. Simple, direct, ridiculously effective. 4 minutes of this, and your mind becomes a pattern-detecting machine. The brain learns the same way muscles do, under light, steady tension, never under torture. Now comes the part that makes every adult nervous and every child delighted: imitating sounds. Minutes 11, 12, and 13. Repetition with intention, not perfection. But hold on. No inventing sentences. No trying to be Shakespeare in Mandarin. You're only going to repeat the phrases or words you heard, nothing more. And before your brain tries to escape through the nearest window, think about this. You've imitated accents before, just for fun. You've repeated songs without knowing what they meant. You've memorized movie lines, which means you're already good at this. You just forgot. So let's run a quick experiment. Say this quietly or mentally if you're in public and don't want to look like a malfunctioning Russian spy.
Repetition isn't stupidity, it's neural engineering. Good. Now another. Pick a simple word in another language you know. Merci, hola, grazie, hello, konnichiwa, and say it 3 times with intentional rhythm. Feel that shift? Your brain starts to play, and when the mind plays, it learns faster. Do you learn better when you're tense or when you're curious and relaxed? Exactly. So right now, choose any word in the language you're learning and say it 3 times slowly and once quickly. Do it now. Yes, now, not later. Felt that? Congratulations. That was a real training. Don't try to sound native yet. Try to sound like someone who isn't afraid to learn. Fluency doesn't come to perfectionists. It comes to persistent, awkward people who keep showing up. Now for the final 2 minutes. The gold that turns this technique into a powerful process. Minutes 14 and 15. Minimal explanation plus tracking.
You'll do 2 things. 1. Summarize what you understood in 1 sentence. Doesn't matter how simple it is. It can be, I understood 1 word. I caught the rhythm. I noticed a repeated verb form. I didn't understand anything, but my brain recognized sounds. Any of these is a neural victory, because whoever explains understands, and whoever tries to explain and fails discovers exactly what to improve next. That is literally the essence of the Feynman technique. Now the second part. 2. Mark your progress. A slash, a check mark, a simple done. No complex journals, no spreadsheets, just a 1 in your physical or mental calendar. You want the secret of progress? The brain loves endings. And when you close a cycle, it rewards you and says, let's do it again tomorrow. Now imagine this, 30 days of this, 15 minutes a day. Nothing heroic, nothing dramatic, just behavioral science plus human curiosity. You don't magically become fluent. You become inevitable. And inevitably, one day, you'll open a video in that language, smile and think, I understood this without even trying. On that day, you'll remember this moment, this first training, this first step, and you'll realize that learning a language was never about talent. It was always about method and present. Now tell me, are you ready to come back tomorrow and repeat? Because your brain only needs you to say yes once a day, and today, you already did. Now drop a simple comment below to lock in today's learning. I train my mind every day. And if you want to go further, tell me, which language are you going to train with this method? Because what you do in the next 15 minutes can shape who you become in the next 15 years. Leave a like, and if you're new here, hit subscribe. There are more videos like this about learning faster, thinking better, and building a mind that works like a living laboratory. And if you like using your brain for something better than memorizing phrases, welcome to the right place. You know, people sometimes ask me how I learned to think the way I do. They assume there's some secret, some trick I picked up somewhere, but the truth is, I don't think I'm particularly smart. What I did learn, though, and this took me years to figure out, is that most people don't actually think, they just accept. Let me tell you what I mean by that. When I was a boy, maybe 10 or 11 years old, my father used to take me for walks in the Catskill Mountains. We'd walk through the woods, and he'd point at birds. One day, he pointed at a bird and said, "See that bird? In Italian, it's called a chuto lapitida. In Portuguese, it's bom da peda. In Chinese, it's chung long ta." Then he'd pause and say, "Now, you know in all those languages what that bird is called, but you still don't know anything about the bird. You only know what people call it in different places. Now, that bird, if you watch it, you'll notice it's always pecking at its feathers. Why? Because there are lice that eat the protein in the feathers, and the bird has to clean them off. The lice eat the protein. They lay eggs. More lice come. The bird spends half its time just staying clean. That lesson stuck with me my whole life. Knowing the name of something is not the same as knowing something. And most of what we call education is really just learning names, learning labels. But thinking, real thinking, means asking what's actually happening. I noticed this later when I was at MIT and Princeton, sitting in advanced physics classes with some of the smartest students in the country. We'd be learning about, say, quantum mechanics or electromagnetic theory. The professor would write equations on the board, beautiful equations, and everyone would copy them down carefully into their notebooks. Then, at the end of class, someone would raise their hand and ask, "Professor, what does this equation mean?" And the professor would explain it again using different symbols, different mathematical language. And the student would nod, satisfied. But I'd sit there thinking, wait, what does it mean? Not what does the equation say? What's actually happening in the real world that this equation describes? See, there's a difference between knowing something and understanding something, and most people, even very educated people, confuse the two. They think because they can repeat what they've been told, because they can pass a test, because they know the technical terms, that they understand, but they don't. I'll give you an example. After the war, I worked on the atomic bomb project at Los Alamos. I went to Brazil to teach physics at the university in Rio. Wonderful place, beautiful students, very serious about their education. But I noticed something strange. These students could recite entire textbooks. They'd memorized everything. But when I'd ask them a simple question like, what happens if I shine light through a Polaroid filter at a certain angle? They couldn't answer. They'd never thought about it. They only knew what the book said would happen, not why it happened or what it meant. I started asking them questions differently. I'd say, forget the textbook. You're walking on the beach, and the sun is reflecting off the water. Why is that reflection brighter from certain angles? They couldn't answer. They didn't have the habit of thinking about the world around them. They had the habit of memorizing what they were told. That's when I realized something important. Thinking isn't a talent you're born with. It's a habit you build, and most people never build that habit because nobody teaches them how. So how do you build it? How do you train your brain to actually think instead of just accept? The first thing I learned to do, and I did this naturally as a kid, without realizing it was special, was to always translate what I was learning into something I could see or touch or imagine. When someone told me about atoms, I didn't just memorize, atoms are small particles that make up matter. I'd picture them. I'd imagine them bouncing around, colliding with each other. I'd ask myself, if I had tiny eyes and could watch atoms, what would I see? Later, when I was studying physics at MIT, I did the same thing with equations. People thought I was slow, because while they were racing through problem sets, I'd sit there, sometimes for hours, just staring at an equation. But I wasn't being slow. I was translating. I was asking myself, what is this equation actually describing? If I could watch this happen in real life, what would I see? Sometimes I'd even invent strange little scenarios. Like, when I was learning about electromagnetic fields, I imagined I was the size of an electron, floating in space. What would I feel? If another charge came near me, how would I know? What would push or pull on me? This sounds childish maybe, but it worked, because once I could see it in my head, I understood it. And once I understood it, I never forgot it. Here's the thing nobody tells you. You can't think clearly about something you can't visualize. And most people skip that step. They learn the abstraction first, the formula, the technical term, the theory, and they never bother to connect it to anything real. So it just floats in their head, disconnected, meaningless. And then they wonder why they forget everything a week after the exam. The second thing I learned, and this took me longer, was to always ask, why? Not just once, but over and over, like a child. Children are actually brilliant at this. They'll ask you why the sky is blue, and you'll say, because of the way light scatters in the atmosphere. And they'll say, why does light scatter? And you'll say, because air molecules are small and interact with light waves. And they'll say, why do they interact? And they keep going until you finally admit you don't actually know. We lose that somewhere. We get embarrassed to ask basic questions. We don't want to look stupid. So we just nod and pretend we understand. But that's a disaster. Because if you don't understand the foundation, everything built on top of it is shaky. I remember once, I was teaching at Caltech, and a student came to me confused about quantum mechanics. He said, I don't understand the uncertainty principle. And I said, okay, explain to me what you think it means. And he started reciting the textbook definition, something about position and momentum and Planck's constant. And I stopped him and said, no, don't tell me what the book says. Tell me what you think is happening. And he couldn't. He literally couldn't tell me because he'd never thought about it. He just memorized it. So we sat down, and I said, let's start simple. Forget quantum mechanics for a second. if you wanted to measure where something is like a ball, what would you have to do? And he said, look at it. And I said, right. And how do you look at something? And we went through it. Light bounces off the ball, enters your eye. You see where it is. And I said, now, what if the ball is really, really small, so small that the light you use to look at it actually pushes it when it bounces off? And you could see his face change. He got it. Not because I gave him a better definition, but because he finally thought about what was actually happening. This is the secret, if there is one. Don't accept anything until you can explain it to yourself in your own words, using your own pictures, your own analogies. If you can't do that, you don't understand it yet. And that's okay, but don't pretend you do. The third thing, and this is maybe the most important, is that I learned not to be afraid of not knowing. This sounds simple, but it's not. Most people are terrified of admitting they don't understand something. They think it makes them look dumb, so they fake it. They nod along. They use the right words even though they don't really know what those words mean. But here's what I figured out. The smartest thing you can do is admit when you don't know something. Because once you admit it, you can start actually learning it. But if you pretend you already know it, you're stuck. You stop asking questions. You stop thinking. I used to sit in seminars at Princeton and Caltech where some famous physicist would give a talk really technical, really advanced, and everyone would sit there nodding like they understood every word. And maybe some of them did. But I didn't always understand. So I'd raise my hand and ask a basic question. And sometimes people would look at me like I was simple. But you know what? Half the time, after I asked, 3 other people would come up to me afterward and say, "Thank God you asked that. I didn't understand either." The truth is, a lot of what passes for expertise is just people pretending. They've learned the language. They know which words to use. But they don't actually understand what they're talking about. And you can tell if you listen carefully, because when you ask them to explain it simply, they can't. They retreat into jargon. They make it sound complicated because they themselves are confused. So I made a rule for myself. If I can't explain something to a freshman, or to a child, or to someone with no background in the subject, then I don't really understand it myself. And that's okay. That just means I need to think about it more. There's one more thing, and this might sound strange, but it's been useful for me. I learned to enjoy not knowing, to actually find it exciting when I encounter something I don't understand, because that means there's something new to figure out, something new to play with. When I was at Los Alamos during the war, we were all working incredibly hard, long hours, high pressure. We were building a bomb, after all, and I was getting burned out. I felt like physics had become this heavy, serious thing, just equations and problems and pressure. So afterward, when I went back to Cornell, I decided I was just going to play. I wasn't going to worry about doing important work or publishing important papers. I was just going to think about whatever seemed interesting. And one day, I was in the cafeteria, and some kid threw a plate in the air. And I noticed the plate was wobbling as it spun. And there was a blue medallion on the plate, Cornell's logo, and I noticed that the medallion was rotating faster than the plate was wobbling. And I thought, I wonder why. So I went back to my office, and just for fun, I worked out the equations. Why does the plate wobble that way? What's the relationship between the wobble and the spin? And it turned out to be connected to some deep principles of rotation and angular momentum. And that little problem, that silly thing I did just because it seemed fun, eventually led to work that contributed to my Nobel Prize years later. But I didn't know that at the time. I wasn't trying to do important work. I was just playing. I was just curious. And I think that's maybe the real secret, if I'm being honest. You don't force your brain to think like a genius. You just let yourself be curious like a child. You ask questions. You try to see what's really happening instead of just accepting what you're told. You admit when you don't understand something, and you keep thinking about it until you do. Most people stop themselves before they even start. They think, "Oh, that's too complicated for me," or "I'm not smart enough to understand that," or "I'll just trust the experts." But understanding isn't about being smart. It's about being persistent. It's about caring enough to actually think about something instead of just accepting it. I've spent my whole life around the smartest people in the world. Nobel Prize winners, brilliant mathematicians, incredible physicists. And you know what? Some of them were genuinely brilliant. But most of them were just people who never stopped asking questions, who never accepted something just because everyone else did, who kept thinking about problems even when everyone else had moved on. You can do that. Anyone can do that. You don't need to be special. You just need to care enough to try. So next time someone tells you something, anything, doesn't matter what, don't just accept it. Ask yourself, what does that actually mean? Can I picture it? Can I explain it to someone else in my own words? If not, then I don't really understand it yet. And that's okay. That's just where the thinking begins.